Hello, good day, and welcome to the second of our lectures. The first lecture was on fluid mechanics, but like I talked about in the introduction, the bulk of the semester is going to be on electricity and magnetism. And we're going to start with that today. And so we're going to look at the basics of electric field and electric force. So this is chapter 21 in the Giancoli book. If you're from a different school and you have a different textbook, you're welcome to look on with that. And so let's start with the slide presentation. So what exactly are electric charges? And this goes back to Benjamin Franklin in the 1700s, and he was one of our country's founding fathers, but he was also our first significant scientist. And he studied the nature of electricity. And so some of the things he discovered were that there were two types of charges, positive charges and negative charges. He didn't know about the inside of an atom, so he didn't know the positive charges were carried by protons and negative charges were carried by electrons, which led to some confusing sign conventions that developed in the 1800s, really, and that were counterintuitive based on what we now know about the motion of things, because it's the electrons that do all the moving, and those are the negative charges. Another thing that Benjamin Franklin observed is that like charges repel and opposite charges attract. So you put two positive charges near each other, they will repel each other. You put two negative charges near each other, they will repel each other. But if you put a positive and a negative charge near each other, they will attract each other. So remember when we talked about gravity, or when you learned about gravity in Physics 1, gravity is always attractive under every circumstance. That's not the case with electricity, and it won't be the case with magnetism when we get to that later on in the semester. So again, at the atomic level, positive charges are carried by protons, while negative charges are carried by electrons. The electrons do most of the moving. It takes quite a bit of energy to free a proton from an atomic nucleus. And to get positive charges to move, whereas electrons can move fairly easily. And you can move electrons simply by combing your hair, for example. So it's not a difficult process to move electrons. But to move protons, it's much harder. And that applies for electrical circuits also, that electrons can move very easily through conducting wire. And so it's the electrons that do nearly all the moving. And when we're talking about an electrical current, we're almost always going to be talking about moving electrons. So in general, protons and electrons canceling each other out, leaving no net charge. The electrical force over small distances is much, much, much stronger than the gravitational force. But as you get to a bigger and bigger size scale, the electrical forces tend to cancel each other out. And what you're left with is gravity at the big scale. An object becomes charged if it gains or loses an electron. So an object that loses electrons becomes positively charged. An object that gains electrons becomes negatively charged. In SI units, which are the units we work with in physics, certainly in the international study of physics, the unit of electric charge is called the Coulomb, named for the person who developed the law for electrical, or the equation for electrical force, which we're going to talk about in a couple of seconds. We are not going to define the Coulomb today. Ultimately, the Coulomb depends on the unit of current, or how you define your unit of current. And we won't get to define the ampere until chapter 28. So a lot of electrical units and constants that we talk about get their values from how the current is defined. But that's not something that we're going to get to, or that actual definition is not something we're going to get to until much later in the semester. And one important thing, and this is something we won't get to its conclusion in this semester, but so how you define certain electrical relationships and certain magnetic relationships as well depends on how you define the ampere. But we're going to come across a couple of quantities that are electrical and magnetic that ultimately don't depend on how you define the ampere. And that's an important thing to keep in mind, especially moving forward from this class when you start to talk about things like electromagnetic waves. So some substances allow the movement of charge more easily than others. It's not something as far as why that's the case that's easy to talk about at this level. You really need to get into the quantum mechanics of it to talk about why. And that's more for a modern physics course, which maybe some of you will get to. But basically, we'll leave it here as that we have three types of substances. We have conductors, which allow electrons to move through very, very easily. We have insulators, which essentially block the movement of electrons through them. And we have semiconductors, which allow a moderate amount of movement through them. And so silicon and germanium and carbon are considered semiconductors. Semiconductors are very valuable because they make it possible to regulate the flow of current. And so they have a lot of value in electric circuitry, especially modern electrical circuitry. So there are a couple of ways that you can observe the electric charge. The most obvious way is charging by conduction or by contact, where some sort of friction scrapes electrons off one object, leaving it positively charged, and then transfers it to another object, which then becomes negatively charged. And so that's something you can observe. And so you can observe the attraction between the positive object and the negative object. Or you put two negative objects towards each other, you can see the repulsion. So that's the most basic way. But you can also observe electrical charges through something that's doesn't actually involve moving the charges off an object. And so if the electrons can move at least a little bit within an object, you can observe something that's called charging by induction or polarization. So I'll do a drawing of this so that you can see what's going on. So let's say you have there we are. So let's say you have a neutrally charged object that's a conductor, or the electrons can move through it fairly easily, and it's balanced so that it can move. So it's balanced on a needle so it can move. So you expose it to a positively charged object. So what's going to happen? Well, if the electrons can move through this freely, they're going to be attracted to the positively charged object. So the electrons are going to move to the left in this case. And so there's going to be a shortage of electrons on the other side, so it gains a positive charge. So what then happens? Well, you've got a negatively charged side and a positively charged side. So that's where polarization becomes in. You have a negative pole and a positive pole. But you have negative charges at the side facing the positive charged rod. So between them, you get attraction. So what happens when you put a negatively charged object near the same conductor? Well, here, the negatively charged objects are going to repel the electrons. So the electrons are going to move to the right. And so you'll have a negative charge on the right side of the object. And that leaves a positive charge, or a net positive charge, due to the absence of electrons or the shortage of electrons on the left side. So again, you have the positively charged side facing a negatively charged rod, and you're left with attraction. So when you're talking about induced electrical charges, you're always going to get an attractive force, whether you put a positively charged object near the neutrally charged object where the electrons can move freely, or whether you put a negatively charged object. So it doesn't matter. You always get attraction. And that's a very important concept. It actually comes into play when we're talking about magnetism, too. With magnetism, you're working with north poles and south poles, but you get a similar relationship. And so typically, when you think of magnets, they're always causing attraction. And so something similar to this is happening, and that's why you always get attraction. But let's move back to the lecture slide. So that's what an induced charge is. So now we're going to get to the mathematics of it. And so, again, I mentioned that the SI unit of electrical charge was the Coulomb. Well, it was named for a French scientist named Coulomb, who was working at the very beginning of the 19th century, the early 1800s. And he discovered that electrical forces, or electrically charged objects, exert a force on each other that's mathematically very, very similar to gravity. And it's similar that you have an inverse square relationship, at least as far as the magnitude goes. You have a universal constant, and you have the magnitude of the two charges influencing the force. So with like charges, the direction of the force on one object is away from the other object. And with opposite charges, the direction of the force on one object is towards the other object. So again, like charges repel, opposite charges attract. And so let's look at the equation. We'll look at the first equation, or the first two terms in the equation. So F is equal to K Q1 Q2 divided by R squared, and then multiplied by a unit vector R. So let's talk about each of these things in turn. K is a universal constant. It's called the Coulomb constant, and it's approximately equal to 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. So compare that to capital G, the universal gravitational constant, which was 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. So you're talking about a much higher value for the constant. And that's important, that electrical forces tend to be quite a bit stronger than gravitational forces. Usually we don't observe them because the positive and negative charges cancel each other out at the real world scale. So you have K, this universal constant, you have Q1 and Q2, the magnitude of the two charges, or not just the magnitude, but the sign of the two charges as well. Notice that for the vector equation, you're not concerned with absolute values, that the signs matter. And then for R squared, again, you have the inverse square law, that it's the force is proportional to the inverse of the square of the distance between the objects, and that's just like gravity. You can write this an alternative way. If you look at the last term on the right. So that's KQ1, Q2 divided by R3 multiplied by the R vector. So in the first term, there's an R unit vector over R squared. In the second term, it's R, the vector R, divided by R cubed. So the vector R has a magnitude equal to the distance between the two objects, and it points from the object exerting the force to the object that the force is acting on. And so you can write this equivalently as r hat, the unit vector, over r squared. You can also write that as simply r over r cubed. So mathematically, they're equivalent. Typically, if you're only interested in the magnitude, you're going to use the unit vector notation. But if you're looking at the full vector for the electrical force, sometimes it's easier to write it the way it's written on the right. And as the problems get more complicated, it generally becomes easier to write it the way it's written on the right. So again, the Coulomb constant is equal to 8.9875 times 10 to the negative, or 10 to the positive 9. That's important. Newton meters squared per Coulomb squared. The unit vector r hat points from the charge exerting the force to the charge on which the force is acting. And the vector r does as well. The unit vector is the vector r with the arrow on top of it divided by its magnitude, so that the magnitude of the unit vector is simply 1. So if both charges have the same sign, the force vector will point away from the first charge and vice versa. So that's repulsion. If they have opposite signs, the force vector in the second charge will point towards the first charge and vice versa, which is attraction. So let's go back to this equation. If Q1 and Q2 are both positive, or they're both negative, then the product is going to be positive. And so the force points in the direction of the r vector, which again, away from the force, or away from the object that's exerting the force towards the object that's the force is acting on. So it's pushing the object away. If Q1 and Q2 are opposite charges, meaning one is positive and one is negative, then the product of Q1 and Q2 is negative. And that means the force is in the inverse or the negative direction of R, which means that it points towards the object that's exerting the force. So again, you have attraction. So if Q1 times Q2 is positive, the force is acting away from the source of the force, or the source charge. And if the product of Q1 and Q2 is negative, the force vector points towards the source charge. So that's how you look at that. So let's do our first example. So what is the magnitude of the force a 25, so it's a positive 25 microcoulomb charge exerts on a 2.5 microcoulomb charge 28 centimeters away? So we have two positive charges. So let's clear the last drawing. So we have two positive charges. We know that R is equal to 28 centimeters, and it's a positive 25 microcoulomb charge and a positive 2.5 microcoulomb charge. And so the problem asks for the magnitude of the force. So if it's asking for the magnitude of the force, that means the signs involved don't matter as far as the magnitude. But because they're both positive, we know they're going to repel each other. But it's asking for the magnitude of the force. So that's F without the arrow. And so that's the magnitude of the force vector. And that's equal to K times the absolute value of Q1. Again, if you're only interested in the magnitude of the forces, the signs don't matter. Now, granted, they're both positive in this case, but if one of the charges were negative, we would the absolute value signs would matter. But again, when you're talking about the magnitude of the vector, that's always going to be a positive number. And so you have these terms, and so that's, and since we're only working to two significant figures, we can write this as simply 9.0. And the easiest way to think of the Coulomb constant is 9 times 10 to the 9. So 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. And then you have the product of the two charges. And so that's 25 microcoulombs and 2.5 microcoulombs. So micro is 25, or is 10 to the negative 6. So that's 25 times 10 to the negative 6 coulombs. And as a general rule, I think I talked about this a little bit last time, and I'm sure I'll talk about this more than this as well. As a general rule, you want to write the terms of the equation in their standard SI units so that your answer comes out in SI units. So if you write K in terms of Newton meters squared per coulomb, and you write your charges in coulomb, and then you write R in meters, so that's 28 centimeters, that becomes 0.28 meters. So you divide 28 by 100. And don't forget, you're squaring that. So if you put all these numbers in their SI units, then the answer will be in SI units, which is newtons, and that's what you want. So you pull out a calculator and you do the math. And so what I get when I do this to two significant figures is 7.2 newtons. Okay, so that's the answer that you wind up getting. And that's a fairly measurable amount of force, that if you have even microcoulombs, which may not seem like a large amount of charge, but you have a microcoulomb charges, you can get a noticeable amount of force out of them. And so that's definitely a force that you can observe. So the repulsive force is something that you can see. So getting back to the lecture. So Coulomb's law obeys what's called, the electrical force obeys what's called the superposition principle. So the electric forces due to different charged particles add together vectorially. So if you have multiple charged particles exerting force on another charged particle, you need to add the force vectors together to get the resultant force acting on that object. And so if you think back to vector addition, going back to whatever Physics 1 class you took, and you probably had some sort of lab experiment using a force table where you added vectors together, this applies to that. And so you're going to be adding vectors together if you're talking about multiple charged objects exerting a force on another charged object. So that's something to keep in mind. When we do the recitation, and I think for homework as well, you're going to be asked to solve a superposition principle problem. And they can get fairly lengthy, but we won't go over that here just yet. So with that, let's move on to what's called the electric field. So gravity and electricity have some similarities, but they also have some differences. They're both field forces, which means they don't require the objects to be in contact with each other in order for their motion to be influenced, in order for the force to be present. So a contact force is when you're pushing on something or lifting something or pulling on something. Those are contact forces. Your hand is actually in contact with whatever object you're pushing, pulling, lifting, whatever, throwing. Those are all examples of contact forces because your hand is in contact with the object you're exerting the force on. Field forces don't require contact, but they can still affect the motion. So one way of looking at it is that A massive object creates a gravitational field around it, and charged objects create electric fields around themselves. And an object that's moving within the electric field is going to be, a charged object that's going to be moving within the electric field is going to be influenced by that field. It's useful in a couple of circumstances. One, when the object that's moving within the field is small enough that it's not affecting the overall field. So if you think on the big scale, you think a satellite orbiting the Earth, that has mass, but it's not going to affect the Earth's gravitational field all that significantly. Similarly, the Earth's orbit around the sun is not going to affect the sun's gravitational field all that significantly. So with gravity, you're usually talking about one really big object as the source of the gravitational field. So at this level of physics, the gravitational field is really not all that important, and you almost never see it referred to in an introductory physics class. Whereas the electric field is a different beast altogether, because you can have many charges creating an electric field. And so you have a test charge that by itself, if the electric field is strong, the isolated test charge moving within the electric field might not be big enough to significantly affect the overall electric field. And plus, the other thing with electricity and with gravitation, another important difference, gravity is universally attractive. The electric field the electric force is not universally attractive. It's attractive some of the time, it's repulsive some of the time. And because of that, sometimes it's easier to talk about the field rather than the force, simply because the field only depends on the source charges rather than the direction of the field depends on the source charges rather than the object that the field is acting on. And so what we're going to do is define a source charge or source charges and a test charge. So the source charges are what create the electric field. So it could be a big individual charge or big single charge. It could be a combination of a bunch of charges that are creating the electric field. And then the test charge is the charged object that's moving within the electric field. And so we have QS and we have QT. So the magnitude and direction of the electric field vector only depend on the source charge or the source charges. So that's an important formalism. So, and again, we usually don't discuss gravity this way, again, because it's universally attractive. And so you're not necessarily adding an element of confusion. You're not trying to make things less confusing by talking about the electric field. But also, usually with gravity, the field is being generated by one really big object. And so the field concept doesn't simplify the analysis, at least not at the introductory, the physics 1 level. But with electric fields, or with electricity, it can. And so you'll see that more as we go on. We'll see that there are a lot of important physical quantities that are related to the electric field, either directly or indirectly. And so it's very important to talk about the electric field for that reason. But the force, the electrical force between two objects, or the electrical force acting on an object in an electric field can be written as the test charge multiplied by the electric field vector. Or the electric field vector is equal to the electric force vector divided by the test charge. Notice there's no absolute value sign on the test charge, which means its sign matters. So if the test charge is positive, the electric force and the electric field vector will point in the same direction. If the test charge is negative, the electric force and electric field vectors will point in the opposite direction. And so that's important to keep in your mind as we're moving forward with this, both in this chapter and in the next couple of chapters. So again, a positive test charge is accelerated in the direction of the field. The force and the field vectors point in the same direction. The negative charge is accelerated in the opposite direction. So again, with a negative test charge, the force and the field vectors point in opposite directions. And so the electric field vector is equal to the electric force vector divided by the test charge, which means in SI units, you can express the electric field strength in terms of newtons per coulomb. And that's usually how it's expressed. We'll also see when we get to chapter 23 that the electric field can be expressed equivalently in SI units as volts per meter. But we're not going to talk about volts just yet. That's something to keep in mind and file away for the time being. So let's get to another example. A downward electric force of 8.4 newtons is exerted on a negative 8.8 microcoulomb charge. So what are the magnitude and direction of the electric field at the position of this charge? So let's go back to the whiteboard. So again, we have a downward electric force. So we know the direction of the electric force. So there's a downward electric force. And it's equal to 8.4 newtons, and it's exerted on a negative 8.8 microcoulomb charge. So the magnitude is 8.4 newtons. The charge is equal to negative, and that's 8.8 microcoulombs. So we have a negative charge here. And so we're asked for the magnitude and the direction of the force. So the force is acting on a negative charge. So the negative charge, if the test charge is negative, so the test charge is this object that's moving within the electrical field. And so if the test charge is negative, the electric force and electric field vectors point in opposite directions. So the electric field vector points upward. So we know the direction of the electric field, and then we're asked for the magnitude. And so the magnitude of the electric field vector is equal to the magnitude of the electric force divided by the magnitude of the test charge. So to figure out the magnitude of the electric field vector, you don't need to be concerned with positives and negatives. So you have the absolute value sign here. So the force is equal to 8.4 newtons divided by 8.8 times 10 to the negative 6 coulombs. So again, we're writing this in terms of, we're converting from microcoulombs, and a micro means 1/1,000,000th, or 10 to the negative 6. And so we're writing it like that so that we can express our answer in terms of microcoulombs. So you do the math. And so that's 9.5 times 10 to the 5 newtons per coulomb. And so that's the magnitude of the electric field, and the direction of the vector is upward because it's in the opposite direction of the force. So before we move on, I want to talk about this a little bit further, just conceptually. So there's an electrical force acting downward on a negative charge. So there are basically two ways that can happen. So positive charges will attract it. So there could be positive charges below the negative charge attracting it. There could be negative charges above the test charge repelling it, or there could be some combination of the two. So that you have positive charges underneath it or negative charges above it, or some combination of the two. Well, how does that affect the electric field? Well, notice the electric field points away from the positive charges and towards the negative charges. And that is true universally. So we can talk about the electric field as always pointing out of positive charges and always pointing in towards negative charges. So that's very important conceptually. And that will come into play quite a bit as our study of electric field continues in this chapter and next chapter. So again, the electric field vector always points out of a positive charge and into a negative charge. So let's go to another problem. The electric force on a positive 4.20 microcoulomb charge is, and this is unit vector notation. I'm assuming you've taken physics with calculus that includes the vector analysis. And so in unit vector notation, there's a unit vector I that points in the x direction or along the x-axis, a unit vector j that points in the y direction or the y-axis, and a unit vector k that points in the z direction, the positive z-axis. And so if you define the x-axis as to the right, a positive I hat would mean it points to the right, and negative I hat would mean it points to the left, and so on like that. So unit vector notation is something that's going to come up quite a bit in this class. We're going to still do quite a bit with vectors in this class, not just with electricity, but even more so with magnetism. You're going to work with vector quantities a lot. So let's set up this problem. So we'll go back to the whiteboard. Meant to do that. All right. So clear this. And so we're given that the force is 7.22 times 10 to the negative 4 newtons in the j hat direction. So we start with that, and it's in the j hat direction. And the test charge is equal to positive 4.20 microcoulombs. So the electric field, again, it's newtons per coulomb. The electric field vector is equal to the force vector divided by the test charge. Now, the test charge is positive, but the sign does matter. If the test charge were negative, we would have to include the negative sign here because we're asked for the vector. We are not asked for the magnitude of the vector in this problem. So that's 7.22 times 10 to the negative 4 newtons, j hat. So again, it's a vector equation, so don't omit the j hat term. And then 4.20 times 10 to the negative 6 coulombs. So again, you get your answer in terms of newtons per coulomb. And that gives us 1.72 times 10 to the 2, or 172 newtons per coulomb. And again, there's no negative term, so it's still in the j-hat direction. Because the test charge is positive, the electric field vector and the electric force vector point in the same direction. So moving along, how do you calculate the electric field based on the source charges? So if you have a single source charge, the electric field vector is equal to k, the Coulomb constant, multiplied by the source charge, divided by r squared, and it's in the r hat direction. So the r hat, or the direction of r, is different here than it was last time, or a little bit different. When you're talking about the Coulomb's law of force, the r vector points away from the object exerting the force. Here, the r vector points away from the source charge. So mathematically, basically the same thing, but there's a little bit of a difference. So there's a subtle difference you need to be wary of, that you're always pointing from the source charge to the test charge. And again, you can write this as kqs over r cubed times the vector r, rather than so writing it like that as opposed to writing it as a unit vector. And again, sometimes the harder the problems get, the easier or the relatively simpler it becomes to write the electric field vector the second way, divided by r cubed, but multiplied by the vector r. So the vectors point, whether it's r hat or r with the arrow, they point from the source charge to the test charge. And so the electric field always points away from a positive source charge and into a negative source charge. So if the source charge is negative, then the field vector is pointing in the negative r direction, which is into the source charge. So that's that's just the mathematically formal way of explaining that electric field points out of positive and into negative. And of course, the superposition principle applies when determining the electric field as well. So if you have multiple source charges, you're going to vectorially add them together. And that's one of the conveniences of unit vector notation. That's if you write the vectors in unit vector notation, it's easy to figure out the resultant vector, which you can still express in unit vector notation. But that's what we're doing with this. So let's go to another example. So determine the magnitude and direction of the electric field 16.4 centimeters directly above an isolated 33.0 times 10 to the negative 6 Coulomb charge. So it's positive, and if they don't specify a sign for the charge, you can assume it's positive. So again, let's go back to the whiteboard, and let's write this out. So we have a positive charge, and so the electric field always points out of a positive charge. It looks something like that. And we're evaluating the electric field at a point a certain distance above the source charge. And this is another advantage of working in terms of fields, that you don't actually need to have a test charge present for there to be an electric field and for you to be able to evaluate the electric field. So that's another benefit of working with the field notation. So we know the distance is 16.4 centimeters. And the source charge is positive 33.0 microcoulombs. And again, micro is 1/millionth or 10 to the negative 6. So we want to find the electric field, the magnitude and the direction. So the direction is up because we're directly above, you're looking at a point directly above the source charge. The source charge is positive. So the electric field points out of the source charge and it goes up to point P. So that's the direction. And usually it's easier to figure out the direction first. And then the magnitude is equal to K times QS divided by R squared. And if we're interested in the magnitude by itself, we can just we can put absolute value terms around the QS, meaning that we're only going to get a positive number as an answer for the magnitude. So K to 3 significant figures is 8.99 times 10 to the 9 Newton meters squared per Coulomb squared. QS, the source charge, is 33.0, and that's 10 to the negative 6. Again, you write everything in standard SI units, your answer will be in standard SI units, which in this case is newtons per coulomb. And so R is 16.4 centimeters. So in SI units, that's I can do that better. You can write that as 0.164 meters, and you're squaring that. And so that gives you 1.10 times 10 to the 7 newtons per coulomb. Okay, so that's how you figure out the magnitude and you figure out the direction. Usually if the problem's written like that, it's easier to figure out the direction first. So it's coming out of the positive charge. And then figuring out the magnitude, again, you just use the formula, but you put absolute value signs around the charges. Okay, so you can also visualize the electric field using things called electric field lines. And so field lines follow the direction of the electric field at a given point. And we're actually going to look at field lines in a lab experiment. It won't be until next week, but we'll have an experiment where you'll be asked to map electric field lines. So the field lines follow the direction of the electric field at a given point. The number of lines per unit area is proportional to the strength of the field. Lines begin on positive charges and end on negative charges. And the number of equally spaced lines drawn coming from or going to a charge is proportional to the charge. No field lines can cross each other. So how does that look visually? So you have a positive charge. By itself, drawing the field lines is easy. So the field lines will come out of the positive charge. Similarly, if you have a negative charge, the field lines will point into it. Now, let's say you have a positive and negative charge together. What happens is you will wind up connecting the field lines. And so it looks something like this. So it looks something like that. And so you have the lines coming out of the positive and into the negative. You can see that the field is strongest near the two charges. And that you actually have a bit of space. It's relatively weak in between the charges. But you have this, and as you can see, you get further away from the charges. The field goes to zero, and you can kind of see this based on how these lines are being drawn. So there are a couple of conceptual ways that you can just see how this works. So it's useful, at least at the basic level, of visualizing how fields work. But what happens if you have two like charges? Now remember, field lines can't cross each other. So you start with positive charges, and it works the same with positive as it does with negative. Two positive as it does with two negative. You're just changing the directions of the arrows. And so you have a positive charge over here as well. But what happens is, instead of bending so that it goes into the negative charge, the field lines are going to get bent so that they don't intersect each other. And so remember, that was one of our rules. The field lines do not intersect with each other. And so it looks like that. And so if you put more field lines in, they will bend out and away from the positive charge so that they don't intersect. And one of the consequences is, if you were to draw a line straight between the two positive charges, you would get no field lines crossing it. And remember from our definition that field strength is a measure of how many lines are crossing it. Well, if you don't get any field lines crossing it, no matter how many lines you're drawing, the field there has to be zero. So there's a straight line down the middle where the field is essentially zero. And certainly directly in between, the field is going to be zero. If you go up start to go up or start to go down, eventually you do get a significant component in the vertical direction for the electric field. But certainly directly between them, the field is zero, that there are no points in the immediate vicinity of that. And otherwise, there's definitely not any horizontal component of the electric field, or component pointing to the right or to the left if you were to draw a vertical line in between them. And so these are things that you can visualize, that the field gets weaker as you go away from the first positive charge, gets to zero when you're between them, and then starts to increase again as you approach the second positive charge. So that's basically how this works. So it's a useful way of visualizing. It's without getting into the math, just to show how the relationships work and how you can expect them to work when you start adding charges to the field, so that it's not just one. There may be multiple charges influencing the field. And again, it doesn't give you a mathematical answer, but it allows you to visualize things. And if you can visualize things, the better you can visualize things in your head, the easier it is to figure out how to do the mathematical part. So now we're going to go to a film, a quick clip about a very important experiment. This experiment determined the fundamental unit of charge. It was devised by a scientist named Millikan I believe it was the early part of the 20th century, and essentially used oil droplets to figure out the most basic unit of charge. And we're going to talk about that a little bit after the film clip is over. But let's see if I can get this up so that you can see it.
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhered to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thomson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
Okay, so let's talk about what happens. So the friction gives these charges oil droplets. The air drag on the droplets is so high that the terminal velocity is very small, but it makes it possible to figure out the mass of the droplets by figuring out their terminal velocity. So it's related to the mass, and so you can figure that out. The electric field moves the oil droplets upward between two charged particles, counteracting gravity and air drag. So if they're moving, there's going to be an air drag force acting upwards. And so the electric force is also designed to force the object upwards. And so when you stop the velocity, then, when you suspend the object in the air, then the electrical force, Q times E, is equal to the droplet's mass multiplied by the acceleration due to gravity. Once there's no motion involved, there's no air drag involved. Just like if there's no motion, there's no kinetic friction. And you can think of air drag as being a kinetic frictional force. So you have M, the mass of the droplet, times G, which we know, is equal to Q times E, and you can figure out what the electric field is, or you can measure the electric field, then you know all the variables, and all you need to do is solve for Q. And what Millikan figured out was that the charge in the droplets was always an integral multiple of 1.602 times 10 to the negative 19 coulombs. So we're going to define a variable E as the fundamental unit of charge as 1.60 times 10 to the negative 19 coulombs. And so the charge of a proton is positive E, and the charge of an electron is negative E. So protons and electrons have equal and opposite charges. So the total charge on any object is equal to plus or minus capital N times E, where N is the total number of either missing electrons or extra electrons. So if it's gained electrons, it's going to have a negative charge. If it's lost electrons, it's going to have a positive charge. But either way, the magnitude of that charge is equal to the total number of electrons that have either been gained or lost, multiplied by that number E. So that's a very important fundamental constant. E is equal to 1.60 times 10 to the negative 19 coulombs. And so, outside of high energy particle accelerator collisions, that's the smallest charge you can get. So let's do an example. How many electrons make up a charge of negative 38.0 microcoulombs? So let's get back to the whiteboard. So we know that Q is equal, we're talking about electrons, so that's negative NE. And we're asked to solve for N. So that N is equal to, bringing the negative sign over, so that's negative Q over E. And so that's negative, but the charges themselves have negative 38.0 microcoulombs. And it's easy to get microcoulomb charges, and you don't need special equipment to get that level of charge. You can rub a balloon on your hair and get an exchange of charges on the order of microcoulombs. So how many electrons does that come out to be? So Q is negative 38.0 microcoulombs, and then E, and we should write this in correct units. And then E is always written positively. So 1.60 times 10 to the negative 19 coulombs. And so you put those numbers together, and that tells you how many electrons we're talking about. And so that becomes, to three significant figures, 2.38 times 10 to the 14. So that's how many electrons we're talking about. So 10 to the 9 is a billion, 10 to the 12 is a trillion. So that's 238 trillion electrons in that charge of 38 microcoulombs. Okay, so that's one example. Here's a second example. What is the repulsive electrical force between two protons 4.0 times 10 to the negative 15 meters apart from each other in an atomic nucleus? So protons are stacked together in the nucleus. Obviously, there has to be an additional force, and it's called the strong nuclear force, that cancels out the repulsive electrical force, because the electrical force between the two protons is pretty strong, and it would be repulsive. And if there weren't some other attractive force, they would just repel each other and push each other away, and no atoms would ever form. So you have the Coulomb force, so that's K times the charge of the two objects. So they each have a charge E. So we'll write that as KE squared divided by R squared, where R is simply the distance between them. And so we are given it in two significant figures. So we can write K as 9.0 times 10 to the 9 Newton meters squared per Coulomb squared. And then you're multiplying by E again. So that's 1.6 times 10 to the negative 19 coulombs. And you're squaring that. And then you're dividing by 4.5 times 10 to the negative 15 meters. And you're squaring that term. So you have a couple of very tiny numbers in the numerator and the denominator that you're going to be squaring. So how does that affect the end result? So what I get is 11 newtons. So that's a very, very, very large force given the size scale we're talking about, 2 protons in the nucleus. And so the strong nuclear force has to be even stronger than that to hold the protons together. Obviously, the strong nuclear force is not something we're going to talk about in this class. But it's worth talking about the electrical repulsion at that level. Which brings us to one last example. What are the magnitude and direction of an electric force on an electron in a uniform electric field of strength 1,920 newtons per coulomb that points due east? So the first thing we're going to do is, and this goes back to physics 1, where typically when we talked about geographical coordinates, we defined the positive x direction as east and the positive y direction is north. And if you need the third direction, the positive z direction is up. So we're going to keep that formalism here, which means we can write the electric field vector as being equal to 1920 newtons per coulomb. And since it points due east, and we've defined that as the positive x direction, we'll add the I hat term. And so we're asked for the electric force on the electron. So the electric force is QT multiplied by the electron, or rather multiplied by the electric field, excuse me. So the test charge is the electron. So that's negative 1.60 times 10 to the negative 19 coulombs. And again, it's the vector equation, so the signs matter, no absolute value signs. And multiplied by 1,920 newtons per coulomb. So that force equals 3.1 times 10 to the negative 16 newtons. And that might seem like a very small force, but you have to keep in mind the electron is not very massive. It's on the order of 9.11 times 10 to the negative 31 kilograms. So you're still talking about an acceleration on the order of 10 to the 15 meters per second squared. So it's still, that force is strong enough to produce a large acceleration in the electron. Okay, so that brings us to our last slide of the day. So we've talked about if you have one source charge, you have a simple and straightforward equation. If you have multiple source charges, you have the superposition principle. So you're adding the electric field of the individual source charges together. If you have a continuous distribution of source charges, you're going to need to integrate. And so, again, you can write the equation in a couple of different ways. So you can write it using the unit vector, or you can write it using R arrow over R cubed, and you need to figure out the distribution of the source charges, or the source charges as a function of position. And then you're going to be integrating over that position. We will talk more about that relationship next time. We're going to introduce a concept called Gauss's law. And one of the things we're going to do with Gauss's law is show how it takes complicated integral problems, some of which we're going to do to demonstrate for you, and converts them into simple algebra problems. And so you'll see how much simpler it makes them. And then we'll go to some applications where we're just going to do it using Gauss's law. But it's worth seeing the integrals in order to fully understand just how powerful Gauss's law is. So that's going to be the subject of our third lecture, Gauss's law, which is chapter 22 in the Giancoli book. And I realize some of you are from different schools. You might be using a different textbook, but that's okay. I'm not going to force anybody who has a physics with calculus textbook to buy another one. But keep in mind that just make sure you know what where in your textbook, if you're using a different textbook, the material we're covering can be found so that you can look at it. Otherwise, we are done for today. And like I said, our next lecture will be on Gauss's law. The next lecture will actually be after the first exam. The first exam comes up fairly quickly. It's going to be next Tuesday. So it comes up fairly quickly. It's just going to be on the first two chapters. So if you have any questions, don't hesitate to email me. And we will talk again soon. Thank you very much.